Hello, and welcome back to the course in Physics for Engineers. We are still on the chapter on electromagnetism. So let us first review some concepts before we proceed with this lesson. So in the previous lesson, we have discussed about Faraday's law given by these equations. And in the previous chapter on electrostatics, we have discussed about how there is force on current carrying conductors. And this force is due to the external magnetic field B, and it's forcing the current I. So this is a cross product. So the force is just Li cross B. So for this lesson, we will be talking about motional EMF. EMF generated due to motion of a conductor. So the motional EMF can be derived from Faraday's law. So this is Faraday's law. So if we apply Faraday's law to this system here, so we have a conductor here in the shape of a letter C shape. And then we have another conductor here with length L, and this is actually movable. So this conductor here is fixed, but this conductor is movable. And this actually creates a loop. But the area of this loop is changing depending on where you move the conductor. So if you move the conductor, this conductor, in that direction with velocity v, then the area of this loop is changing. So in this case, the magnetic field is into the page. So if you will see, the magnetic field is uniform at all points in the loop, and it's directed into the page. So that one. Now, if we apply Ampere's law, so since there's only one loop, so n is equal to 1, and since the direction of the area vector and the loop, so we align the area vector and the loop, and the area of the loop in the same direction, so meaning cos phi is 0, and cosine phi is just 1, cosine 0 is 1. So we have just d dt VA. Now, the area of the loop is the length, since this is a rectangle, so it's the length of the loop times the width of the loop. So length times width. Now, since the length of the loop is constant, it's fixed, only the width of the loop is changing, then we only take the derivative of the width with respect to time. So we have negative b times the length times dw dt. Derivative of the width with respect to time. And the derivative of the width with respect to time is basically just the velocity of the this rod here. So that one. And then substituting that one, we get the motional EMF for a conductor of length L moving with velocity v through a magnetic field perpendicular to the rod. So this is what we call the motional EMF. So this is the EMF generated by a conductor of length L moving with velocity v in a uniform magnetic field B, which is perpendicular to the conductor or to the loop. So the negative sign again implies that the direction of the induced EMF is opposite the change in area. So meaning, in this case, the induced EMF is actually out of the page. So if this is the direction of the induced EMF, meaning the direction of the induced current and induced EMF and induced electric field is in a counterclockwise motion in this specific example. So what happens now to our rod here? So our rod is actually becoming a source of EMF. So the upper end of the rod becomes a positive terminal, and then the lower end of the rod in this case becomes a negative terminal. So take note, the induced current flows out from the positive terminal of a battery and goes into the negative terminal of a battery. So basically, a rod moving through a uniform magnetic field B will actually become a source of EMF. They will actually become a battery. So the rod actually here becomes a battery. And if we analyze that in terms of the force, so this is your rod. So your rod contains positive and negative charges. And if the rod is moving in this direction, then there will be a force on the positive charge, Q V cross B. So V is in that direction, B is into the page, so therefore, this is the direction of the force, upward. So all positive charges will be forced upward, and all of the negative charges will be forced downward, because the negative charges are opposite sign, meaning the force is in the opposite direction. So using right hand rule, so that one, so this is your velocity, this is your magnetic field, V cross B equals F. So F is upward. So in order to find the positive terminal for a rod, for its EMF, the positive terminal of the EMF is found by crossing V and B, the velocity and the magnetic field, V cross B. So V cross B to determine the positive terminal. And of course, the opposite of that is the negative terminal. Okay. So let's have this example. So suppose the rod in the figure is 0.10 meters long, moving at 2.5 meters per second, and the resistance of the loop formed, the closed loop here, is 0.030 ohms. So the magnetic field is into the page and has a value, it's constant and uniform. It's a value of 0.60 Tesla. So find the magnitude of the induced EMF, induced current, and the force acting on the rod. So let's first find the induced EMF. Okay, but before that, let's determine which is the positive and negative terminal of the rod. So of course, V cross B. V is on that direction. B, this is V, velocity, this is magnetic field, and this is the force. Right hand rule. So the positive terminal is upward, or in the upper side, and the negative terminal is in the lower side. So meaning this is now basically a source of EMF or a battery. So there will be current in this direction. The current is counterclockwise. So we can also align the area vector with the magnetic field, and then in this case, since the area vector is increasing, therefore there will be an induced EMF in the opposite direction. So the induced EMF is actually out of the page, and that will generate a counterclockwise EMF or current. In the same manner of analysis, analyzing where's the positive and negative terminal of this rod, which became a battery. So we use the EMF, motional EMF formula, negative VBL. So 2.5 meters per second, 0.60 Tesla, 0.10 meters, and all of those units combined will give you a unit called volt. So you have negative 0.15 volts. So again, the negative sign implies that the direction of the induced EMF is in the opposite direction as the magnetic field. So the induced EMF is out of the page, opposite the direction of the magnetic field, which is into the page, and actually opposite the direction of the area vector also, because in this case, it's the area that is changing. So the direction is counterclockwise. So the magnitude is 0.15 volts. So therefore, the induced current is just EMF over the resistance. So EMF over the resistance, you have 5 amperes. Okay. So you have a 5 ampere current flowing through our loop here. So the 5 ampere current actually also flows through this rod here. And the direction of the current is actually upward. Along the rod, the direction of the current is upward. Now, if you have a current carrying conductor and it is exposed to an external magnetic field, there will be a force. The force is Li cross B. So, Li cross B, or the magnitude of this is just L times I times B, since the current and the magnetic field has an angle of 90 degrees. It's perpendicular. So this is cross product, so sine phi, sine of 90 degrees is 1. So Lib. So the force is just Lib. And the force on this rod is actually directed using right hand rule. This is I. The I current is upward. The magnetic field is into the page. So I cross B. Therefore, there will be a force going to the left. So substituting all the values. So the force is 0.30 newtons. And its direction is to the left. So using right hand rule, Li cross B. So the magnetic force on this current carrying conductor exposed to an external magnetic field. The external magnetic field is into the page, so I going up, B going into the page, so therefore the force is in this direction, using right hand rule. Okay, so todo lang. Okay, let's have another example. So in this case, we now have a loop and then a moving rod. So the moving rod completes the loop. It's still moving to the right with the velocity v. And then the magnetic field now is still uniform and constant, but it's now out of the page. So the dots that you see here are just magnetic field lines pointing out of the page. So in this circuit, the length of the rod is 0.36 meters. The resistance of this resistor here is 45 ohms. We will assume that there will be no resistance for these connecting wires. So the total resistance of the loop is just due to this resistance here, or resistor here. And the magnetic field is 0.650 Tesla out of the page. So letter A. Is the induced current in the circuit clockwise or counterclockwise? What do you think? So the direction of the area vector here is in this direction. So the area is increasing, so therefore there will be an induced EMF in that direction. So therefore the direction of the induced EMF and induced current is it's clockwise. So the direction is actually clockwise. So you can actually also do V cross B to determine the positive and negative terminal of the rod, which now becomes like a battery or a source of EMF. So V cross B, so the velocity is going to the left, the magnetic field is out of the page, so meaning there will be a force downwards. V cross B is downwards, so meaning the positive charges or the positive terminal of this rod is downwards, the negative terminal is upwards. So if the positive terminal here, meaning the current will flow out of here and then in that manner. So still the same analysis, still the answer is the same. The current and the EMF is clockwise. Okay, for letter B, at an instant when the resistor is dissipating electrical energy at 0.840 joules per second, what is the speed of the bar? So what does this mean? At the instant when the resistor is dissipating electrical energy at 0.840 joules per second. This is the power lost or power given or power dissipated to the resistor. Power delivered by the current to the resistor. 0.840 joules per second. Joules per second is just watts. 1 joule per second is just 1 watt. So basically this is power. You are given the power. So given the power, so by the way, this is the direction of the induced EMF into the page. So given the power is just I squared times R. So meaning we can now solve for the current. It's just square root of power over R. So substituting the values, power is 0.840 joules per second or 0.840 watts over 45. Resistance is 45 ohms. So therefore the current that flows through our circuit here, the induced current is 0.137 amperes and its direction is clockwise, a clockwise direction. So knowing the current, we can now solve for the EMF. The EMF is basically just negative I times R because of Faraday's law. It's negative I times R, which is also equal to negative VBL. So meaning the unknown here is the velocity, the speed of the bar. We know the current, we know the resistance, we know the magnetic field, we know the length of the rod. So we can now solve for V. And V is just IR over BL. Substitute all the values and convert them to standard units. The final unit is meter per second. And you will get a value of 26.3 meters per second. So the speed of the bar actually depends on these factors here: the current, the resistance, the magnetic field, and the length of the rod. Okay. So let's have a final example. Suppose you have, by the way, I forgot to emphasize that usually this is what we call a slide wire generator. It's a generator because it generates current. In this case, it generates direct current, DC or direct current. So it's a slide wire generator because you're actually just sliding the wire over the rails. You're sliding the wires over the rails to generate current. So actually, you see, you have actually seen these types of generators, such as in bump cars or in trains. They usually actually use slide wire generators. Rail guns. You want to research about rail guns? They basically use some kind of slide wire generator. So a slide wire generator is composed of 3 slide wires. So these are the 3 slide wires. They can slide along the rail. So this one and this one. So this is wire number 1, wire number 2. Wire number 1, wire number 2, slide wire number 2, and slide wire number 3. And they both have different lengths, and they both have different velocities, magnitude of velocities, and different directions. So these are their different directions. So the magnetic field is directed into the page. It's uniform and constant. And then find the current flowing through the circuit if the circuit has a total resistance of 10 ohms. So use the direction for the positive current and EMF as a reference. So you will use now this direction, the counterclockwise direction, as the positive EMF and positive direction for current. Okay, before we solve this problem, we need to determine, since these slide wires, slide wire number 1, number 2, and number 3 will now become sources of EMF, will now become batteries, we need to determine where are their positive and negative terminals, so that we can determine what is the direction of the current generated by each of these batteries, whether it's clockwise or counterclockwise. So for number 1, slide wire number 1. So V cross B. V cross B. V, velocity is upward. Magnetic field, my middle finger is into the page. V cross B is equal to F, the force. So meaning positive charges will be forced upward. So this will be the positive terminal, and this will be the negative terminal of slide wire number 1. So meaning the current due to slide number 1 will be in this direction, will be counterclockwise. Okay, slide wire number 2. So V cross B. So meaning this will be the positive terminal. This will be the negative terminal. So meaning the current generated by slide wire number 2 will be also counterclockwise. And then the last slide wire number 3, V cross B. So meaning the positive terminal is this part here, and the negative terminal is this part here. So meaning the current generated by this battery, by this source of EMF, by this slide wire generator, is in this direction. So this is a counterclockwise direction. Okay, so the current now for generated by slide wire number 1 will be positive because it's counterclockwise. Same with slide wire number 2, it's also positive. But for slide wire number 3, it's negative because it's the positive terminal is here. So this will have a clockwise manner, which is opposite of our reference here. So the total current now in the circuit will be positive. I1 is positive, I2 is positive, and I3 is negative. So we're just like doing a Kirchhoff's rule here. Okay, so we now have, how do we now solve each of these individual currents? So we use Ohm's law. So EMF over R, where the EMF, the magnitude of EMF due to slide wire number 1 is just V1B times the length of slide wire number 1. Velocity of slide number 1, the magnetic field is constant, then the length of slide wire number 1 over the resistance. And you get 0.025 amperes or 25 milliamperes. Do the same for slide wire number 2 and slide wire number 3. So you add these two, you subtract I3, and you will get 0.005 amperes or 5 milliamperes. So basically, you can imagine this as 3 batteries. 3 batteries were in, for these 2 batteries, you connect their positive terminals. And here, the negative terminals of these 2 batteries are connected. So basically, their currents will compete with each other, and there will be just one current left flowing to the circuit which is 5 milliamperes. So 5 milliamperes is the current flowing through all of the loop in the circuit, including all of the sources of EMF, your slide wire generator. So 5 milliampere current flows through our closed loop here. Okay. So that is it for motional EMF. Oh, by the way, sorry. Before I emphasize, I forgot to emphasize that since the value of our total current is positive, meaning it's in the counterclockwise direction. So that one. So that is the end of this lesson, the chapter on motional EMF. So I will see you again in the next lessons for chapter 14. So bye for now.